So you at this point know the basics of an atom, right? We know that an atom is the smallest piece that you can break down any matter into. And all of those atoms, right, are organized on the periodic table of elements. So this front little page of notes here, they have fluorine as an example. One unit or one piece of fluorine is called an atom, and that atom is unique and different to any other type of element that we know, okay? So the focus for today is to look at what important information does the periodic table tell us about atoms of each element. So before we get going though, vocabulary, just kind of know an element is basically like the purest form of matter. It can't be broken down into any simpler of a substance. If you break it down any simpler than this, like you would not have an element, you'd have subatomic particles, which we'll talk about here a little more today. So, just to review, what is an atom? It's the smallest part of a chemical element that can exist. It really comes from like the ancient Greek word atomos, which basically means like it can't be cut anymore. Like I said, if you cut anything, if you split an atom, then you no longer have that element. Elements that you know, probably oxygen, hydrogen, nitrogen, they all are made up, or they all are atoms. One unit of it is an atom. So I will link this in the resources. I can't remember if I've had you watched it before, but it's basically like just how small is an atom, and it's a really great kind of like look into and giving you a sense of just how tiny it is. And then there's a spot on your notes for you to go ahead and answer these couple questions and how they compare an atom to a blueberry, an atom to a grapefruit, and then they even look at the nucleus itself as well. So topic 2, right? How has our concept of an atom changed over time? Like how have we believed it's looked or what it's part of? And it's really changed a lot. So the very beginning starts in 1803. And at the beginning, we compared it to a billiard ball, right? Like think like a pool table with all of the like hard round balls just, you know, kind of clunking together. Basically, we know that at this point, atoms were not able to be cut down anymore, but we didn't know much more. It was just like a solid mass. It was just really, really tiny. Then we evolved a little bit more in our understanding, and it comes to the Thomson theory. So about 90 some years later, we start to think of the atom as more like a chocolate chip cookie, right? Where we have different pieces. We have the actual cookie itself, and then we have the chocolate chips inside of it. The chocolate chips were representing positively charged and negatively charged particles, but we thought they were just kind of randomly placed and they were all floating everywhere. Then, about 10 years later, we become even more sophisticated in our understanding, and we start to compare it to a cherry pit, okay, or a cherry with a pit. Basically, that development of the nucleus starts to come about, and we realize that most of the atom is in this nucleus. It's in the center. That's where it's like the most dense and the heaviest. And then we realize, but there's still stuff floating around the outside, although we don't know exactly too much about it, but it's mostly positive on the inside, and then that outskirts negatively charged. Then 1913, we start to compare the atom to a solar system where you have the nucleus or the sun that's fixed in the middle, and then you have these electrons or these negatively charged subatomic particles that float in a very recognizable pattern around the outside. Just like planet Earth orbits around the sun, electrons orbit around the nucleus, which you know has protons and neutrons in it. Our current theory is most like a cotton ball, right? So we know that there's the nucleus, it's got the protons and the neutrons in it, but the electrons on the outside is now, we equate it to like this cloud. It's basically like a storm, and we never really know exactly where an electron is. We just know that they're moving at really high speeds, and it's really actually very confusing. And so when we start to study the atom, we are actually going to look at this Bohr model to kind of help us understand it a little bit better, realizing that it's not 100% accurate. So I've been using the term subatomic particle at this point a few times. Sub, think like under or below, and we have three kind of like smaller pieces to the atom. We have protons, positively charged ones, neutrons, neutral, they don't have a charge, and electrons. Those are the three parts that make up an atom, okay? And one thing that, before we move on to the next part, we measure, or we find the mass, essentially we're just going to call it like the weight of these things, we measure it in AMU, an atomic mass unit. So protons. Protons are like the fingerprint of your atom, okay? The idea is that no atom of any element is the same. So for example, hydrogen atoms only look like hydrogen atoms, and they will not have the same number of protons as oxygen, phosphorus, potassium, okay? So just like when we learn in the human body, every person's fingerprint is unique, the number of protons an element has is unique. Protons are positively charged, and we use this little P with the plus symbol on it to represent it, and it has a mass of 1 atomic mass unit. Neutrons are neutral. We use that symbol N with the 0 by it. They also weigh 1 atomic mass unit. And neutrons, basically, they just add mass to the atom, but since they are neutrally charged, they don't add a charge positive or negative. Electrons are that third subatomic particle. They are negatively charged. We use the symbol E with a little negative sign, and they are basically so small that they basically don't have a mass. So we say that they weigh 0. All right, so like I mentioned, we are going to actually use that Bohr model or the solar system model to kind of help explain and understand the atom a little bit better, because our current theory is really difficult. So right here, you don't have to color it in if you don't want, but basically, we've talked about this a little bit. Protons, positively charged ones, and neutrons, these green ones, are found in the nucleus of the atom. Then the electrons float around the outside, and right now we're going to put them in little orbitals or little rings to kind of help us track them a little bit more easily. So the next question, topic 5, is what is an isotope of an atom, okay? Think of an isotope like different flavors of an ice cream, right? Ice cream is still ice cream, but you could have chocolate, vanilla, strawberry. So here we have carbon is our flavor of ice cream, but we can have carbon 12, 13, or 14. And essentially, if you look kind of closely here, you'll notice that this number that's attached to the end is the number of protons and neutrons added together. So here we have 6 protons, 6 neutrons, it's carbon 12. Electrons never change, all right? Carbon 13, and I think you need to record these numbers, right? Still has 6 protons, because if it has a different number of protons, it's a different element, right? Protons are like the fingerprints. It's very unique to that element's atom. The thing that changes is the number of neutrons, and this one happens to have 7. So 6 plus 7, that's how you get the 13, carbon 13. And then here, you kind of can guess it, still 6 protons, but 1, 2, 3, 4, 5, 6, 7, 8 would give you 14. Again, the electrons never change, the protons never change, just the neutrons, and that's how you get like the different flavors of carbon. Here, that's what I mentioned, right? Different flavors. And later on today, when you are working on kind of like the little assignment, it's going to ask you, sorry, this is cut off, what is the isotopic notation? And basically, you will just know how many protons and how many neutrons does it have and add them together. So you would have carbon-12, carbon-13, carbon-14, whatever it is. All right, so on the periodic table itself, like in each individual square, There are a couple different things to know. First of all is the atomic number. They might not always be here in the corner, but you know it's the atomic number because it's the whole number. It never has any decimals with it. It basically is like the identity or, like the ID of the element. So here we have fluorine, and this is really important. This number, your atomic number, tells you how many protons an element has. So fluorine has 9 protons. You would notice if you look at a periodic table, it's the only element that has 9, right? Hydrogen is number 1. It only has 1 proton. Okay, helium is number 2. It only has 2 protons. So whatever that number is up in the corner, I think yours might be at the top, or wherever, it might be at the bottom too. I don't know. It's the whole number. That is the number of protons that element has. And again, the only element with 9 is fluorine. It also in some way will indicate to you what state of matter it is at room temperature, solid, liquid, gas. The ones on the back of our agenda uses color coding, but it also might use a symbol. It has the chemical symbol later on in this trimester when we start to look at how elements interact with one another. Rather than writing out fluorine each time, we would just use the letter F or the symbol. And it's usually 1 or 2 letters, and it usually is what it starts with. Sometimes it's completely random, like gold is AU. Obviously, also the element name. So right under it, fluorine is actually what it's called. Usually Latin or Greek words. And then finally, they have the atomic mass. And this is something that is really important here. The mass is how much, basically, on average, if you took all of the different flavors of ice cream, so if it had carbon 12 or carbon 13 and carbon 14, right, with their changing numbers of neutrons, that's on average how much they weigh. This number is important because this number helps us to determine, along with this number, how many neutrons we have. So let's look here, okay? Your atomic, or your mass number, basically, I'm going to kind of back up here, is when you take this atomic mass, so 18.998, and you round it to the nearest whole number, right? So here we would round it to 19, okay? And I want to remind you, flipping back here, that protons weigh 1, neutrons weigh 1, electrons weigh nothing. So this number 19 represents basically how many protons plus how many neutrons, right? Because it's a 1-to-1 ratio, so it's fine. We know the two of them added together equal 19. We also know, I told you this up here earlier, that fluorine has 9 protons. So we can do a little simple math. If there are 19 protons and neutrons in the center of this atom, and 9 of those 19 are protons, that means that 10 are neutrons, okay? You can pause on this screen to kind of read exactly what I was saying here a little bit more if that didn't quite make sense. So, your sum it up questions. I will create a separate video kind of walking you through a couple of them, but I would like for you to practice doing 1 through 10 so you can kind of get a little bit of a better understanding of what we talked about today.